Well, she said it's isn't wait. It's Friday the and so this
It's supposed to.
No. It's just I want you guys to not hate me. Can you imagine if I like specifically said there's not going to be a quiz? And then
I don't know why you did it every morning.
okay, so a quick extra credit opportunity for the undergrads. So the grads all have to go to the colloquium this Friday anyway. But the undergrads, this Friday at 4, the colloquium's at 4 this week, right?
45.
What's that? 3:45. So Friday at 3:45 is the MSE Distinguished Alumnus Lecture as part of our department colloquium series. And this year it is the distinguished alumnus speaker is Mark Shirley, who is now the CEO of Finkel Steel International Corporation, and he's done a lot of really cool stuff with. He used to work for Griffin Wheels up near Akron, where they made cast railroad wheels that actually outperformed forged wheels. And he's going to be giving a bit of a technical talk on steel, but also about sort of his experience going from a metallurgist into management and as an executive. So go to that, and then there'll be a sign-in sheet out front. It's in the big room on the second floor of McQuigg. What's the number? 264. Yeah. So it's in that room, and there'll be a sign-in sheet up front with a little sign that says. So if you go to the colloquium, there'll be some extra credit points.
Would it be extra credit for WE grads?
Oh, yeah, because you guys aren't required to go. You got the welding colloquium to go to. I don't know, that sort of makes it. We'll just say it's extra credit for the undergrad. All right. Okay, so we started going through looking a little more carefully at the equilibrium or metastable iron carbide phase diagram, and we pointed out that for the most part we're going to be concerned with the formation of ferrite and cementite and how this happens, but there's other carbides that can come up, such as the Hate carbide, right? And we identified important reactions in the system, and we said that the paratectic reaction doesn't have too much of an effect, but really we're mostly concerned about things that are happening near the eutectoid region. Right? And we looked at structures that come from hypereutectoid and hypoeutectoid. And if we're light on carbon, then we get regions of ferrite with pearlite interdispersed. If we're hypereutectoid, we have proeutectoid cementite that forms on the prior austenite grain boundaries, and then the rest of the prior austenite grain transforms into pearlite. And we'll be talking a lot more about pearlite on Friday. So we have two main mechanisms of transformation, or two, I would say not mechanisms, because each one of these has its own different mechanisms, but two main classes. Reconstructive, which are basically diffusion mediated transformation, and then displacive, which are transformations that involve a invariant shear or a plane strain. And we also introduced this notion of para-equilibrium nucleation that says these things are happening at a time scale so that carbon can easily diffuse, being an interstitial, but substitutional solids, the substitutional elements, just physically don't have the time to diffuse. So we're not at a true thermodynamic equilibrium, we're at a para-equilibrium state. Okay. And that the ferrite, proeutectoid ferrite, nucleates heterogeneously at the austenite grain boundaries, and that they typically, the ferrite nucleates with a preferential orientation relationship with one of the austenite grains, right? And it forms this Kurgyumov-Sachs orientation relationship, where we have the 1-1-1 plane on the gamma parallel to a 1-1-0 type plane in the ferrite, and the close packed directions lining up, right? So basically, this can sort of be envisioned as a 90-degree rotation, about a 2-1-1 plane, and it's worthwhile to take the time to sketch out these planes, right? Exactly what is related to what. Now this Kurgyumov-Sachs, I said it's going to form preferentially with one of the two grains, right? But this is a very low energy relationship, right? It maintains that the close packed directions don't actually change. This is a low energy interface that has virtually no mobility, right? So this relationship is formed with one of the two austenite grains. Then our ferrite will grow into the other, right? Leaving this relationship fixed, and then the boundary between the ferrite and the austenite grain into which it's growing is generally going to be a high energy or non-coherent interface. We also looked at two different morphologies, right, which grow in different ways. The first is ferrite allotriomorphs, right, which grow on the grain boundary and they follow the grain contour. And then idiomorphs, which nucleate heterogeneously from an inclusion in the crystal, but they grow, this is basically a single crystal of ferrite, and they grow and they have these faceted shapes that reflects the symmetry of the ferrite crystal, right? And so these nucleate without any contact with the austenite grain boundaries. Right. So here we can see allotriomorphs that have nucleated and started to grow, and they haven't connected to form a complete film here. And here's just a micrograph of ferrite idiomorphs hanging out in the interior of the austenite grain. Okay, so both of these occur by true diffusional mechanisms, right? So we don't have any shear, we don't have an invariant plane strain shape change like we will with the Widmanstatten structures, right? And the growth rate is either diffusion controlled or interface controlled. We're going to assume diffusion control for our analysis, but the important thing here is this, because it's diffusional, it means we need thermal activation, right? We have an activation energy that's associated with these. We have a R star value that's associated with these, right? The same as for aluminum. Here we're nucleating these primarily heterogeneously, but this is still only going to occur at high homologous temperatures, so near our eutectoid temperature, right? If we get too low, we're going to grow Widmanstatten. If we get even lower, it's going to be bainite. If we get even lower in temperature, it's going to be martensite, right? Yeah.
How does Widmanstatten vary from idiomorphic?
Oh, we'll get there. Yeah, that's the next set of stuff that we got here. Okay, so because it's diffusional growth, right, our main limitation is going to be our diffusion in the carbon in front of the interface, right? And so we're rejecting carbon from the ferrite, right? We got a partitioning. So we've got a diffusion field that's building up in front of our growing ferrite, right? And the effect of this is going to be that as our ferrite gets larger, the extent of this field gets larger, and that's actually going to retard the growth because our carbon has to diffuse over longer distances, and our thickness of our ferrite increases as a dependency on the square root of time, right? Meaning that the growth rate slows down. Right? So I didn't put the complete derivation here, but this is basically the general idea behind modeling this, right? So in the ferrite, we have a carbon concentration here. In the austenite, we have a carbon concentration here, if this is our overall alloy composition, right? So this is our composition in the austenite region. We come down, we start to partition by the lever rule. So that means if this is ferrite here, this is the ferrite austenite interface. Here's our overall carbon concentration of our austenite. We now have this diffusion profile out in front. So we can model this by saying that the rate at which the solute is being partitioned has to be equal to the flux, the fusion flux from the interface, right? So that means that all of the carbon that's coming out of the ferrite has to go through that interface, right? It's just a balance, right? And then this, we give our conservation of mass, and we can combine that with the diffusion equations, and we get a PDE that looks like this for the change in the position of our interface with respect to time as a function of our diffusivities and our concentrations and the current position of the interface, right? If we solve this PDE, which I know you guys all love the math, but I'll skip over it for now. That's more of a transport phenomena coursework. But we end up with the position of our interface, our distance goes with the square root of time. And so if we can take the derivative of this with respect to time and look at the rate of our change of the distance. And we can see it becomes 1 over the square root of time. So that as time goes on, our growth rate essentially goes to 0, right? So what does 1 over square root look like? It's curve that looks something like this, right? Because remember, our position goes asymptotically, gets flatter and flatter as we go out. Right? So if we assume we're nucleating heterogeneously, but let's just simplify the problem and think about it for a second. Just say we've got like a JMAC scenario going on. We're nucleating at a constant rate, right? So then we nucleate, they start to grow, and as they grow, the growth rate slows down, right? But our nucleation rate is still sort of constant, right? So if these were to grow and fill up our space, what would it sort of look like? Yeah. Are they going to be sort of all equiaxed in that they all, or I mean, not all equiaxed. What's our size distribution going to look like? Are we going to have large distributions or small? Is it going to be uniform? Is it going to be skewed? It's definitely going to be skewed, right? Because only the very earliest ones are going to grow. Right? There's a lot of catch-up time, right? Nuclei that appear later, right, are growing with a faster rate, and the bigger ones, their rate keeps slowing down, right? So eventually, there's a lot of time for catch-up, right? So if you think idiomorphs that are in the center of the grain, you have sort of a reasonable dispersion of inclusions for them to nucleate on, right? You're going to have them all be about the same size when in a cross section, right? As opposed to something that's nucleation limited and growth slows down, right? Then you're going to have a couple big ones. Yeah.
So I have 2 questions. One, this is all assuming, right?
This is assuming diffusion control. Yeah.
All right. So I don't remember.
So if we go to interface control, which is like the massive transformation, which we'll do next. So massive ferrite's interface control because you're not changing composition.
Well, so the question, I guess, is if this is just talking about the growth of one interface, how do you put nucleation together? I'm sorry.
Well, so I just said we know it nucleates heterogeneously, but just for the sake of a thought experiment, let's assume that we have JMAC-like conditions where the nucleation rate is constant, right? Just for a thought experiment as to what the structure would look like. But that's not realistic, right? We know that these nucleate heterogeneously.
Yeah.
Right. Was that your?
Yeah, I guess I was going to ask.
Okay.
It just sounds like homogeneous.
Yeah, no. I was just thinking of sort of what the structure, right? How does this growth rate tie back to sort of what we see in the micrographs, right? And that we don't tend to see idiomorphs with huge size disparities within the inside of the grain, right? We tend to see them all about, right, sort of the same sorts of size, right? But thanks for that introduction into massive ferrite. Right. So if our carbon content is low enough, right, and if we can cool our alloy quickly enough to avoid partitioning, but slowly enough to avoid martensite, right, we can get a massive transformation, right? So that's reconstructive, a diffusion-mediated transformation where our ferrite is the same composition as our austenite, right? And that's only going to depend on short-range diffusion because we don't have everything is the same composition, right? So we don't have this carbon. We're not partitioning carbon out from our ferrite. We don't have this diffusion field out in front, right? So it's only atomic jumps across the growing interface, right? So it's interface. Yeah.
How does that work out relative to the free energy diagram? Because if you have that one phase from one to another, wouldn't you need to change composition?
Yeah, so what does that imply?
Yeah.
Right? Right, so notice we had so this is our austenite, right? And our ferrite, and we're saying this is an equilibrium transformation, right? So our chemical, and this is our composition, say, or you can be a little off. Basically, what that means is we need to have a flat free energy curve like this, and our potential needs to be a double well, but not skewed, right? So whereas with a lowering in free energy, you would have a potential that's asymmetric like this. Right. So what we need is a potential that looks like this. Right. This is why it only works for low carbon content. Right. And you need to have it needs to be low enough temperature that you have enough driving force that it's going to happen quickly enough without partitioning. Here you need to have your transformation be faster than the diffusion of the carbon. Right? Okay. And so when we have transformations that occur, this massive transformation, we end up with ferrite grains that are larger than our initial austenite grain size. Right? We're not, we typically won't have proeutectoid cementite. Right? And we end up with a large grained equiaxed ferrite microstructure. So how does do I mention? Okay, so how does diffusion-mediated growth went by the square root of time, right? Square root dt. What about just short-range diffusion? It's going to be linear with time, right? Because all you care about is atomic jumps, single atomic jumps, right, across the interface, right? So if you have something that is proportional to the vibrational frequency, right, and the exponential term is constant because we're at constant temperature, right? We're always going to be, our growth rate is going to be linear with time if you think about the equations, right? So we have microstructures that look like this, right? Nice, not perfectly clean equiaxed, right? But notice the carbon contents of these, right? These are ultra low carbon steels, right? 4/10. Oh, this is already percent carbon, right? So 4/1000 of a percent, 2/1000, right? By weight. Okay, so back here, so now we're going to move on to over into the displacive transformations. We're going to talk about Widmanstatten ferrite, and then on to Pearlite, then back to bainite and martensite. So we're sort of hopping a little bit here. Okay. So here we see two different Widmanstatten structures characterized by two different techniques. But what you notice about these are sort of long, needle-like structures, right? You'll see this looks an awful lot like structures we'll see again in titanium, the alpha beta. Titanium, but basically what's happening here is we've got this ferrite that is growing inward from the boundary, right? It's going to appear as long, thin plates or needles, and this is a, where's the umlauts shifted? A Widmanstatten structure, right? And so here is a electron back scattered. So this is colored by the crystal orientation, and notice that within and in between the needles, right, they're generally a low angle boundary, right? There's not a big orientation difference between the Widmanstatten plates, right? They're growing, right? Can you sort of think of what the potential mechanism, right? Where are these nucleating? At the boundaries, right? And we already said that both the cementite, proeutectoid cementite, and proeutectoid ferrite nucleate with a preferential orientation relationship, right? So it's going to have an orientation relationship at that interface and sort of maintains it as we go out. So we have two basic classes. We've got primary Widmanstatten ferrite that grows directly from the austenite grain boundaries, and then secondary that grows from any grain boundary ferrite that happens to be there, right? So any allotriomorphs of ferrite that happen to be there, right? And this is a displacive transformation, right? And so there's a shear associated with this, right? So you can imagine if I'm nucleating and growing, and I've got a shear, right? this is going to give me this sort of, if I have a single plate here and I shear, I now have a jog on my surface, right? Or in my crystal, that this needs to be accommodated. And if this is in a polycrystal, I've got neighboring grains that are pushing back on this. And as this grows, that shear gets larger and larger. Right? You can imagine a deck of cards, right? And I offset one card next to its neighbor by a small amount, right? But if I do that for every card, that shear just builds up and up and up. Eventually, if I take that small shear across the whole deck of cards, I've got a big displacement from one side to the other, right? So this is happening. So energetically, the system can reduce this by not just nucleating one Widmanstatten orientation, but another one with the shear in the opposite direction, right? So as these two grow, the overall effect of them is canceled out, and we just get this offset at the right in the center. So they look like a triangle, right, growing out in, but they're not really one orientation. This is two Widmanstatten needles that come together, and they have the their plane strain shear in the opposite sense, right? And this allows them to grow in a mutually accommodating manner and reduce the overall strain density. Right? Okay. So carbon does partition, right? So again, we're always at para-equilibrium, and we're going to grow at a diffusion. The rate is going to be controlled by the diffusion of carbon ahead of the plate tip, right? Okay. So, unlike idiomorphs, which are growing out in all directions, here we're growing along a plate. So this is the analysis of this becomes similar to the growth of dendrites, right? The tip is always growing into fresh ferrite. Our carbon can be partitioned. Our carbon can be partitioned out the sides, right? Whereas our tip is always growing into fresh austenite, right? But because it's displacive, our substitutional atoms don't partition, right? It's just the carbon, so it's this para-equilibrium that I had mentioned before. Okay. So if our plates grow, right, they have to lengthen and thicken. So we have to consider two different types of boundaries that separate this Widmanstatten lath from the parent austenite into which it's growing. Right, we have the sides of the lath and then the edge or the end. Right? So the sides take a low energy or coherent boundaries, and the sides are much less immobile than the tip, right? So the tip, since it has high mobility, we're going to expect a non-coherent general boundary, right? And so based on this, this simple analysis says we shouldn't expect to see much widening of the lath. We really should only see extension. But we do actually see, right, the laths do grow because eventually they come in contact with each other, right? They grow across, right? So if we go back to our little picture here, right, they nucleate and grow across, but eventually they have to thicken to come in contact with each other and transform. So this won't be the last time you see this, but basically what happens is these lasts thicken as a result of ledges or steps, right? So imagine here, this part of the ledge here is our coherent low energy interface, right? We don't have much mobility orthogonal to this direction, but if our interface is made up of these steps, we have these high energy interfaces here with high mobility. So this can grow by extending the ledge, all of these ledges this way, right? So we can actually have thickening of the laths without breaking that coherent, just destroying the coherency of the interface. We're not forcing that coherent interface to move, right? And then as this grows out this way, extends, we get new steps and ledges that continuously form. Once it stops growing, right, once it's extended as much as it has extended, right, we eventually continue to grow, and once all of these steps have moved all the way across, now we're left with a nice, clean, coherent interface. Right. So this is the growth rate. Right, our lengthening rate is a function of the tip radius. Right. So why does a smaller, thinner needle grow faster than a wider? Higher energy, but how so? Remember, we've got partitioning going on, right? So the smaller the tip, the easier excess carbon can diffuse away from. Right, we're not pushing as big of a diffusion field out in front. Right? So the thinner our tip, the faster the growth rate. Why this abrupt cutoff here? What's that? Say it louder, I can't.
Critical radius.
Critical radius, right? If you get any smaller than that, it's going to dissolve before it grows, right? Right? And then if we look at our thickening rate, right, you see it becomes this. This is time here. This is the half thickness. You can see it's got this jerky motion, right? This is the ledges moving across, right? So thickening is not constant. It sort of goes by sort of these discrete jumps as a ledge grows across. Yeah.
You said earlier that this only happens with small undercooling. So for this kind of growth, would you have to like basically air cool it, or
Air cooling or isothermal hold, right? Right. So we'll put all the different mechanisms. Once we talk about them, we'll sort of put them into perspective as to where they lie on the different sort of temperature range, like where on the TTT diagram we see each of these. Right. So sort of here's a So this is the TTT. Here's the log of time. This is the temperature. Right. So up here, this is the equilibrium. Right. If we're up here, we get ferrite and pearlite pearlitic microstructures, which we'll talk about next. Right. If we're a little bit lower, we get the Widmanstatten ferrite, and then down here into bainite and martensite. So basically, we get this partitioning between reconstructive, or a separation between the nose of the TTT curves here for reconstructive versus displacive transformations. Right, and if we look at the CCT diagram, here's the cooling rates. Right, so if we oh, this was out of place. Shoot, this was I wanted to make this a little earlier, but slow cooling gives us a equiaxed ferritic structure. Slightly faster cooling will give us Widmanstatten. Massive occurs without partitioning, right? So we need to be a little faster for massive, but we're still well over for martensite. The bainite would be in here as well, right? And then this just gives us the changes. So this is the shear strain associated with each mechanism. This is the volume change associated with it. So all of our reconstructive transformations, there's no shear associated with it. But we do have the volume difference, right? The change from austenite to ferrite, right? And the resulting morphologies that come up. Right. So keep this in mind. Okay, so that's the general gist for equilibrium ferrite. Now we need to talk about what's happening with the cementite during this. So actually, before that, let me go to the next slide. Right. So this is pearlite. Right. What do we notice about this? What did you guys think the first time you saw this from the microscope? Probably what, in the sophomore lab?
Pretty.
Did it move anyone to tears, or did anyone thank their deity of choice for creating such a wonderful material that makes our lives so much better? All right. It's complicated, right? It's sort of this messy, squiggly, layered structure, right? I mean, before we sort of jump into details, pull up, think about all the physical metallurgy you've had so far. Think about all your material science. What do you think the properties of this is going to be? The individual phases and the composite as a whole. All right, what about strength? Stronger or weaker? Stronger, why?
Boundaries for where I put various displays.
Yes, these are strong barriers, right? Just think Hall Petch, right? We've made this significantly smaller. The mean free path is a lot shorter for dislocations, but also this isn't a nice clean structure, right? It's a tortuous path, right? That dislocations have to travel through. What about fracture properties?
Typically, composites are tougher.
Okay, so we've got one vote for tougher.
More brittle than iron alone.
Okay, so basically we said composites tend to be tougher. And now you say more brittle, right? What's the reasoning for more brittle?
Bunch of stress concentrations in specifically aligned plates. You're going to basically propagate a crack more easily, I'd imagine.
So you're going to, I would say, nucleate a crack more easily, right? So there's aspects of both answers that are right, because here the crack is going to nucleate easily at the interface, right? But then you're going to break multiple laths, right? So you're going to be absorbing energy in short punctuated bursts between plastic deformation in the ferrite laths, right? What about work hardening? Is it going to work harden faster or slower, or to a greater or lesser extent than plain ferrite? Yeah.
Would it be slower because they're already kind of elongated weight structure? So like the rolling per se wouldn't do as much. Or like making it react streams.
Oh. That's interesting. She said since these plates tend to be elongated, right? When you roll them, you won't, like in the aluminum, and right, we talked about how stringers form in intermetallics. This is going to be a little different, right? Because this is since this is sort of a close zoom in, it appears that everything's sort of aligned, but on the scale of a whole ferrite pearlite colony, right? It's all this sort of swirly stuff. So if you roll it, it's gonna squish. But your dislocations, are they free or are they confined? They're confined, right? So they're not going to be able to wiggle out and recover nearly as easily, right? So we have a higher degree of work hardening, right? So so since I sort of mentioned it, right? The cabbage. So Sir Harry Badisha, the very famous metallurgist at Cambridge. I'm stealing this directly from him, but basically he gives the cabbage analogy to the Pearlite structure, right? And it is true. You can if you imagine that the red here is the cementite and the white is the austenite. In 3D, a Pearlite colony looks an awful lot like the structure of the cabbage. We have these layers of cementite that grow, right? We nucleate, and then we just sort of grow layer upon layer, sort of like an onion, but much more convoluted, right? So you can still peel the leaves off the cabbage, right? But they're much more intertwined than the layers of an onion, right? And it's also a good analogy because even though the individual layers are all crinkly, cabbage is still round, right? So Pearlite forms these nice round equiaxed colonies, but this crazy convoluted structure, right? And just here's sort of an example. Here's what it looks like when you're hypereutectoid, right? Our grain boundary cementite with Pearlite in between, and then if we're at the eutectoid structure, right, and we come down, we can just use the lever rule to determine what the fraction of the ferrite versus the fraction of the cementite is, right, given our carbon content. So for eutectoid steels, we're actually 88% ferrite, 12% cementite, but looks can be deceiving, right? I'm sure most people would have said this is probably a higher cementite fraction than 12%, right? And it's also, remember, this is by weight here, right? So it's 12 weight percent cementite, not volume, right? So we'll stop there. Friday, we will go through the ferrite. Monday, remember,